We're teammate, and we're going to be talking about the communication between IMU and Arduino. My name is Nori.
My name is Chili.
I'm Juchalu.
I'm Alex.
Dan? Blake.
And today we'll be talking about a little background or intro of what our project is, a background of the components that we use, hardware connections, especially the I2C connections, as well as data capturing, which includes programming, and the data output and what that output means.
I will first give you guys a brief introduction of our design project. As we talked about last time, our design is to capture motion of runners and give feedback to runners in order to prove their running posture. And there are two main parts in our project. First is motion capture, and the second is feedback. As for the first aspect, these are sensors and controllers to achieve the motion capture. And to be specific, we need to have smooth communication between sensors and the controller, and a reliable data collection of the sensors. And the sensors, these kinds of sensors are widely used nowadays in our electronic device, like in your smartphones. There are gyroscope and accelerometer in your phones to give you, for example, better gaming experience. And the developers can do more fancy things on this with this hardware. The first picture is the IMU we used in our project. It's IMU MPU 9150. And the chip, the tiny chip, is fabricated by InvenSense, and the module is from SparkFone. It's capable of doing 9-axis measurement. As you can see from the label on the board, the accelerometer has 3 axes, one with y-axis point up, x-axis point to right, and z-axis point out of the board. The gyroscope is measuring the angular speed of these 3 axes. And this chip is also capable of doing the measurement of magnetol field. The axis of the magnetometer is pointing up, the y-axis is pointing to the right, and the z-axis is pointing into the board. The second picture is the Arduino we use in our project. It's Arduino Uno from SparkFone. Some important parts on the board include the power jack. This is the power jack, which provide about 7 to 12 volts power. The USB connection, which is used to program the board, or can be an alternative way to power the board. 14 digital pins, and analog pins, and power and ground pins. One thing nice about these digital pins is that it has its specialized function, which can let us do some more things with this board. For example, for pins from 10 to 13, it can be SPI pins, which can be used to communicate with a Wi-Fi shield. So you can place a Wi-Fi shield onto this Arduino Uno and give the Arduino to capable of go to the internet. And Nori will go deeper into these analog pins and how we use a specialized function in our project.
Okay, so our hardware components consist of obviously the IMU and the Arduino. The Arduino is powered by a 7.4 volt lithium-ion battery, and what you need is 4 wires and obviously the IMU to connect to from the IMU and the Arduino. The 4 wires consist of the connection to the power, ground, clock, and the data transfer. So there's 2 options for powering the IMU, either a 5 volt or a 3.3 volt, which was on the Arduino. And we have to choose the 3.3 volt due to the limitations of the IMU can handle, which is about 2.8 volt to 3.5 volts. And the clock and the data transfer are connected to the I2C bus, which is on the analog side of the Arduino. And what the I2C bus is just two physical wires, or two data lines, called the SCL and the SDA, which one's the clock and one's the data. The clock frequency is about 400 kilohertz, and these two lines are called open drain drivers, which means that they are driven to be output low at all times. So for them to be output high and for the data to be transferred, two pull-up resistors are needed. The values for these resistors aren't crucial, but they usually need to be higher than at least 1.8 kilo ohms, and for ours we use a 2.2 kilo ohm resistor. And on the actual physical Arduino, pin 4 is the SDA data line, and pin 5 is the clock. So for the data transfer, the data is actually transferred in 8-bit packets, and it's called a master and a slave, and the master is generally the clock, which synchronizes the data, all the data transfer. And SDA is obviously the data line. And once all these 8-bit packets are transferred, or each 8-bit data is transferred, an acknowledgement packet needs to be sent. If this acknowledgement packet isn't sent, it obviously means that the data isn't being transferred.
I'm going to go a little bit farther into depth on the I2C bus communication. This top diagram shows an important thing, that the data can only change when the clock is low. So right here, you see the clock goes low and the top line of data is allowed to change. The only time when the data is allowed to change while the clock is high is for the start and stop sequence of the data, or for which you want to transfer. So that's important. And inside the start and stop sequence, you define what address you want to go to, whether it's read or write, and then the actual data. And then when you get done with each communication, you need the stop bit also.
Alright, so this is an actual picture of the wiring. As you can tell, the VCC is connected to that 3.3 volts and ground, and the SDA and the SCL are respectively are in pin 4 and pin 5, and it's connected to the that chip itself is the IMU, but the breakout board obviously gives you a bunch of the outputs, and we're only using 4 of the pins that are allowed in this IMU, one's that ground VCC and the SDA and the SCL line that I was talking about in the I2C bus.
Alright, so one of the problems with the I2C bus is the fact that you're actually only able to, I guess you'd say, attach 2 sensors at a time. So the problem is, the way it's addressed is you're either addressing by setting the address bit high or the address bit low, which, like I said, limits you to 2 sensors, which can pose a serious problem if you're ever going to try and hook up, say, 5 sensors or more. So the way around this is to use a multiplexer. And the way a multiplexer works is you're able to connect multiple sensors over onto the control side of the multiplexer, and you also have selectors over on the right side of the multiplexer that are able to determine what bit you're going to set high to determine what device you're reading to. So on this diagram you can see on the left side over here for all the channel bits, so like I said, you have all the sensors. So say you have 16 sensors all hooked up to the same multiplexer. And then over on the right side you have the selector bits. So those bits on the right side of the multiplexer are actually determining which sensor you're actually communicating with. The way you actually program it is in, like our project, the Arduino code, you actually write whatever bits you're going to write to. So say a byte line of 0001 would equate to the control bit 1 on the left side of the multiplexer. And say you were trying to reach C15, which would be 16, so it would be 1111. And you're able to switch between all of these manually by programming it in the Arduino code.
So I'm going to start talking about a little bit of the software part of capturing data from the IMUs. So Arduino has its own software which we're using, and a very important part of this is the libraries. Libraries are just chunks of code which make your life easier because they have a lot of predefined functions in them. One of the main ones we are using is the MPU 6050 library. The 6050 was an older IMU that only has 6 axes, and someone modified it to get the 9150, so basically they added in the magnetometer. And so we use that to capture the data from the IMU, and then the other very important ones are the I2C library and the lawyer library. That's just used so we can set up the I2C communication. And these two are examples of just how you include libraries. Libraries always have .h on the end, so you just have the # include and then put the name of the library in quotations. Another important part of capturing data is the serial monitor, and that shows all the data that comes through the serial port, and we'll show you an example of that later on.
So for programming our Arduino, we also have many built-in functions. I'm just going to give you a couple that we use that are our main functions. First, we have the serial.begin, and then this gives the baud rate. Baud rate is just how fast Arduino is receiving and transmitting data. We picked about 38,400 because we're doing real time, so we need a high baud rate so we're not losing any data. Next important function, we have Excel gyro.initialize. This just initializes like the accelerometers, the gyroscopes. It's just so that the Arduino can read the data coming in from the IMU. We have Excel gyro.getMotion9. This is built into the library. It's a 9-axis, so then we can read all of the 9 axes that the IMU is outputting. Another important aspect is a string of data, so it's easy to read. It's not one data right after another, because then when you have 9 in a row, and then if you're doing that real time, it gets really messy in a hurry. So the string function just outputs all the 9 data in a row, which gives us the serial.print. This just prints this string of data on the serial monitor, which we'll go over in about 2 slides. It'll show you how it's neater and there's 9 data points right after one another.
All right, so another aspect of the actual programming is the timestamping. So like I said earlier, if you're going to use a multiplexer or you want to be able to use multiple sensors, it's probably a good idea to actually timestamp your data. Timestamping allows you to see the difference between reading between multiple devices. So you're able to see what device is reading from what time and how far apart you're reading between sensors. So the way it works is, as you can see on the right side, long x equals 0.5. It doesn't really matter what you set it to as long as it's a number above 0. Long just really means that you're able to read long digits of data. So if you're timestamping in, say, milliseconds or microseconds, the amount of time actually increases really fast, so you need a longer integer. Micros is actually just the function that's built into Arduino code. So micros means you're measuring in microseconds, and the serial print just means you're printing to the serial monitor. So the data string that Blake was just talking about, you're actually able to timestamp that data string and see the iterations between each data point that's coming in. And lastly, millis is just another function that works along with micros that measures in milliseconds instead of microseconds.
Okay, here's an example of showing the output data. This data is just the raw data showing on the serial monitor, which is just showing whatever that's received by each of the IMUs. Like in the first couple lines showing the IMU is ready to be used and initializing, and you can see here it still says MPU 6050, but like we said earlier, this library was modified to use the 9150, which is capable of measuring up to 9 axes. And this data is not the actual data. We are collecting this just for demonstration purpose. As you can see, this data is barely changed. And also one thing you can notice is the number is relatively large for some axes, and I will talk about why in the next slides. On the header, you will see the first 3 are the accelerometer, and the following 3 are from the gyroscope, and the last 3 are the magnetometer. So this is just the basic equation how we interpret all the data. So for both the accelerometer and the gyroscope, the maximum word length that is capable of measuring is up to 16 bits, which is which gives the IMU the ability to measure up to plus or minus 12G. And for the gyroscope, it's measuring the angular speed, and for the magnetometer, it's measuring the strength of the magnetic field. This is just this, let's say, a simplified version of how we get the useful information out of the raw data, which assumes either the chip is sitting still or the chip is moving at a constant speed. If the human wears the sensor to capture the motion, we actually need to take it into account. We first need to figure out the angle before we can know how much the portion, the projected portion of the Earth's gravity on each of the axes. We need to subtract that to get the actual acceleration of the person. So next slide is showing a more detail into how the accelerometer get all the data. As you can see here, on the first row, we are showing the G values on each of the 3 axes. And on the second row here, we're showing the orientation, which means the angle between the sensor and the particular axis, so X, Y, and Z. As you can see here, so if you have say, a relatively 1G on a particular axis, in the meantime, you will have relatively 0G on the other 2, because the chip is moving, or the data we use is moving at a constant speed or is sitting still. And if you are at 1G and you are relatively at a 0 degree, which means the Earth's gravity is parallel to the axis or is directly aligned with that. So, and you can see by using the 3 data together, we can basically reconstruct the movement or replicate the movement for further analysis. And now I will pass to Blake to walk you guys through a brief video showing how those things work in real time.
Okay, this is a quick video of our setup that we're using right now and how we tested it for real time. There's the IMU right there connected with the 4 wires, as Nori pointed out earlier. She's moving around and it'll display on the serial monitor how the values are changing. So the values are changing from anywhere from negative 16,000 to 16,000, which correlate to like 1G like we referenced earlier. As you can see, it's going pretty fast. This is our baud rate because we want real time, so our baud rate's pretty high. And then this is just, we did it for about 15 seconds. We captured, again, the alpha data on the graphs. And any questions?
Are there questions? Well, I always have. So on this, we're using the I2C communication. Were there other communications available on this particular microcontroller?
Yeah, the other communication is the SPI communication. Unfortunately, the IMU that we're using actually has a digital output, which is used with the I2C bus. So SPI is normally used for, I wouldn't say just analog, but the problem is that the I2C was known to be able to use at least multiple sensors, and we had already set it up that way. And the SPI is also being used currently with our SD card, if we ever set that up, or XP communication as well. So.
Any other questions?